Hi everyone, welcome to Chalk Talks with Lisa, and today we're going to talk about anemia. So let's start with the definition. It's a hemoglobin less than 13 in men or less than 12 in women, but I care less about the exact number and more about why the number's low. So the first thing I do to figure this out is looking at the volume of the cell, so the MCV. And why? Well, it helps me determine what might be causing the anemia. This will make a little more sense if we take a step back and remember what's required to build a red blood cell. Well, first we need DNA to produce the red blood cell during hematopoiesis in the bone marrow. Then we need hemoglobin, which requires proteins, heme, and iron. And then we need the cell membrane, which requires phospholipids and cholesterol. And when cells are abnormally small or large, it's usually because one of these components is affected. And for starters, microcytic anemias are usually due to a defect in the hemoglobin synthesis pathway at one step or another. This means there's enough DNA and phospholipids to create enough cells, but not enough packing material. And the most common cause of this is an iron deficiency. And a lot of things can cause this, the most common being a frank loss of iron, and that usually happens through a GI bleed. There can also be a relative iron deficiency, which happens in anemia of chronic disease, where the body effectively traps the iron inside the cells, usually in macrophages, and this occurs through the upregulation of a protein called hepcidin. You can also have dietary restriction or malabsorption of the duodenum, and that can happen in patients with a Roux-en-Y gastric bypass or celiac disease. More rare causes of hemoglobin synthesis problems are usually with the proteins itself, and that can happen with like a thalassemia, or a defect in the heme synthesis, like in a sideroblastic anemia, which can happen in people with lead poisoning. On the other end of the spectrum, we have macrocytic anemias, where the MCV is over 100 femtoliters. The term megaloblastic refers to a macrocytic anemia with an MCV over 110, and these usually result from a DNA synthesis defect somewhere. And that's why B12 and folate are typically checked in anemia, since they aid in DNA synthesis. Of course, there are also other causes of DNA synthesis breakdown, and that can be from medications like chemotherapies or methotrexate. Or even PPIs, proton pump inhibitors like omeprazole, pantoprazole. These reduce the body's ability to absorb B12 because of the acid changes in the stomach. Non-megaloblastic anemias can happen due to a problem in bone marrow real estate. So like in MDS, so myelodysplastic syndrome, aplastic anemia, or multiple myeloma, basically there's just not enough hematopoiesis happening to produce the number of cells we need. So all of a sudden, those cells that are produced are packed full of hemoglobin, making them larger. So one cause of a macrocytic anemia that's not megaloblastic is actually liver disease. And this also causes a larger MCV or volume for different reasons, primarily due to actually cholesterol metabolism. So cholesterol metabolism happens in the liver. And when this isn't happening properly, you get more cholesterol that's deposited in the cell membranes, leading to larger cells, as well as changes that happen from hypersplenism. So back up from the liver into the spleen. The spleen is all of a sudden eating a bunch of the red blood cells. Another thing you'll see is alcohol can lead to larger cells due to direct toxicity on the bone marrow, and aldehyde, a byproduct of alcohol metabolism, which changes the red blood cell membrane composition and again leading to larger cells. And now you might be wondering, okay, how do we figure out normocytic anemia when the MCV is between 80 and 100? I would say this is the more difficult anemia to work up because it can be due to a number of things. There can be a primary process, or there can be a combination of processes, both in the normocytic camp, in the microcytic camp, or the macrocytic camp. So you have to be a little bit more thoughtful, and your workup is usually going to be a little more broad. So the first thing that can cause a normocytic anemia as a primary process is just frank loss. So let's say you have someone coming in after a trauma, they've lost a lot of blood. Initially, they may not be anemic, but over time, the loss of blood will lead to a reequilibration. Their red blood cells will be diluted, but they'll still be normal red blood cells, leading to a normocytic anemia, so loss. The second thing is destruction. So those are things that lead to hemolysis, and there are so many things that can lead to hemolysis, but ultimately your workup is going to show evidence of this with elevated LDH, so lactate dehydrogenase, which is inside the red blood cells. We also have indirect bilirubin, so a breakdown product of your heme. And then you're going to have increased reticulocytes, so the bone marrow is going to be churning away to make new red blood cells. And you'll also have low haptoglobin, so that's the protein in the blood that helps to eat up the hemoglobin whenever it's in the bloodstream. And these can be caused from processes outside the red blood cells or inside the red blood cells. The ones that are outside the red blood cells are usually things like immune-mediated hemolysis, or even shearing from a mechanical heart valve or severe aortic stenosis. And then there can also be intrinsic causes of hemolysis, like sickle cell anemia or G6PD deficiency, rare, or paroxysmal nocturnal hemoglobinuria. That's a fancy one. You can impress your attendings with this on the wards. That's basically a cause where cells are destroyed by complement. And then there's also non-destructive processes that are typically from early in the microcytic or macrocytic process, or an endocrinopathy such as TSH or low epigen, so in chronic kidney disease, for example. Your workup for anemia ultimately should match what you're worried about, and I hope this video helps demystify the evaluation of anemia. Thanks for tuning in.